Okay, good evening, everyone, and thank you for joining us for Temple's College of Engineering's information session for our major in engineering technology. Just a couple housekeeping items before we get started. This session is being recorded, and it will be posted to our website for future viewing if for any reason you may need to leave the session early, but if you want to refer back to it at any point, it'll be posted on our website in the next day or two, and we'll alert you as to when that's going to happen. So thanks everyone for joining us tonight. I'm going to introduce everyone that's on the call tonight. So myself, my name is Colleen Bailey. I'm the Director of Enrollment Management for the College of Engineering. And also joining us are Dr. Dave Brookstein, who's our Senior Associate Dean, as well as Dr. Dave Reiser, who is an Associate Professor of Instruction in the program. Dr. Brookstein, please take a look real quick.
You do that?
Dr. Brookstein, are you there?
Yeah, can you turn on my camera? Oh, don't worry if you can.
Yep, you should be able to do it now. Go ahead.
Okay. Nope. Oh, yeah, okay. Nope. There you go. I don't know. It doesn't matter. I'll try it again.
That's okay. We'll come back to that. But I want to thank Dr. Brookstein and Dr. Reiser for joining us tonight.
Oh, there it is.
Oh, there you go. So just a quick history about Temple Engineering. So we were founded in 1969. So we just celebrated our 50th year at Temple, which is very exciting. And we have a little over 1,700 students that are currently with us. So the majority of our population are undergraduate students. So we have about 1,500 undergraduates and just under 200 graduate students. Now, depending on the size of your high school, that 1,700 number might sound very large. It might sound normal, but the fact of the matter is that we're one of the smaller colleges within Temple, which is very exciting, and I'll discuss all the benefits of that in just a little bit. The makeup of the undergraduate program, we're about 25% female, which is actually above the national average. The national average for most schools and colleges of engineering is around in the low 20s. So we're really excited that we have a growing female enrollment, and that's been growing very consistently for the last few years. 37% of our students identify as non-white, and we also have students that come to us from throughout the globe. We have 136 international students that are with us. Now, the engineering technology major is based within the Department of Engineering Technology and Management, and there are a total of 40 students within the engineering technology major. There's 30% female and 37% are non-white, and we have 2 international students in the program currently. So this program kind of mimics the undergraduate population makeup. So in terms of why you should consider Temple Engineering for your education, for one, we offer a very high quality engineering education at an affordable cost. And that's very important because higher education is very expensive these days, but core to Temple's mission is offering, again, high quality education at an affordable cost. As you saw before, we're diverse in both our current students and our faculty, and we also have a dedicated team of in-house academic advisors and career counselors. At many universities, you might find that there's a central office that handles both academic advising as well as career counseling, which we do have a central career office, but we have, again, dedicated staff members that just focus on engineering students. So they're there to help you plan out your academic calendar, what courses to select. If you're looking to have someone review your resume, do a mock interview, they're there for that as well. And they can also help you with securing internship and co-op opportunities as well. Because we're one of the smaller colleges at Temple, students have the opportunity to participate in faculty research as early as the freshman year, as a matter of fact. And at most colleges and schools of engineering, you might not see that until you're a junior or a senior. If at all, the priority tends to be more on graduate students. So at the end of the day, what we have at the College of Engineering is you have a small college within a large university. So you really get the best of both worlds. So individual attention, getting to know your faculty, as well as all the benefits that come with being at a large university located in a city like Temple is. We also have a number of student organizations that you can get involved with the College of Engineering. And that's the biggest piece of advice that I always give to students is to get involved, whether in the College of Engineering or at Temple as a whole, because the best students are students who get involved. And these are everything from academic organizations, like you can see here, the ASME, which is the American Society of Mechanical Engineers, to more social organizations like the Society of Women Engineers. And these organizations are all inclusive. So you can join these organizations regardless of what your major is or what your gender identity is. So we encourage students to get involved with these organizations because part of our curriculum and as part of being a good engineer and being a good engineering technologist is all about collaboration. So you're not going to be able to take advantage of collaborative opportunities unless you expose yourself to different types of people and different types of academic needs. So now I'm going to turn it over to Dr. Brookstein, who's going to talk a little bit about what engineering technology is all about.
Okay, thank you, Dr. Bailey. Everybody can hear me? Colleen?
Yep, you're all set.
Okay, so there's engineering and there's engineering technology. And there's a subtle difference between the two. Engineering is more theoretical oriented. Engineering technology is more applied oriented. It's more hands-on. So I'm going to give you some examples that I use in a class right now that I teach that shows kind of what an engineering technologist might be involved in. This is just a small sampling. So if we go to the next slide, we all know we need energy to make heat, which then makes steam. Next, hit the, Colleen, yeah, hit all the way across. Okay, so you start with heat. The heat makes steam. The steam then goes into some kind of device that converts it to mechanical energy. And then eventually that mechanical energy might run a generator to make electrical energy. That's the traditional way that we make electrical energy, okay? If you're burning coal, which we're trying to get away from in this country, you're going to have a lot of greenhouse gases. You're going to have a lot of pollution. If you go to natural gas to supply the heat, it's going to be substantially less in terms of greenhouse gases and pollution. But all that heat is used to make steam. There's another way, though, that you can make heat, which I want to talk to you about today. Next slide. So we've all heard about nuclear reactors, and if you know, we actually have a large nuclear reactor nearby in Limerick, Pennsylvania, where we make we use nuclear energy to make steam, and then that steam goes. Let's see, can I use the? Does my cursor work, Colleen?
No, because I'm sharing my screen.
Oh, okay. All right. Fine. Anyway, it goes into a steam turbine, which then goes to an alternator or a generator. Now, there's a lot of concern about nuclear energy. Frankly, I think a lot of it's unfounded. In the United States, we've never had any kind of major nuclear accident. We did have 3 Mile Island, but no one was hurt from that. We didn't pollute anything. But people think of Chernobyl and what happened in Japan. So the public is generally a little bit afraid of nuclear energy. And it's a real shame because it's a way to make energy that is, I think, very, very clean. But having said that, hit the next button. Next, that's it. So what I've shown here is something called a nuclear small modular reactor. There's a technology that's being developed to make relatively small nuclear reactors. You can see this is by scale. A typical reactor might be 131 feet across and several hundred feet high. That's what they call the concrete containment building. And a small nuclear reactor is substantially smaller, and you can also, and I'm not going to get to all the technology associated with this, but you can have what we call passive cooling in case there's some kind of I don't want to say a meltdown, but in case it gets out of control, which it's not supposed to. And I think this is going to be a big change in nuclear energy in both this country and around the world, and lead to a greater adoption of nuclear energy. So that's what we call non-renewable energy. Non-renewable energy is energy you get from coal, gas, and this is non-renewable too, because eventually the uranium that's used in the nuclear reactor does expend itself and has to be disposed of. So this is what we call non-renewable energy. But the big push nowadays is renewable energy. Go to the next slide. So there are 5 main sources of renewable energy. The first set of sources are what we call intermittent. Hit the button. So like solar energy, which is energy that comes from the sun. Next button. Wind energy. And these are intermittent. Why are these intermittent? They're intermittent because when it's dark outside, you can't make solar energy. The wind's not blowing, you can't have any wind energy. But we also have other sources of renewable energy, and that would be geothermal energy. That's energy that comes from the heat inside the earth, and that's continuous. Biomass from plants, that's renewable. It does create some pollution though, so we want to kind of stay away from that. And then hydropower, like at a dam where you have a generator that is it's turning because of the flow from the flowing water, and that's continuous. So let's go back to intermittent. If you're going to have intermittent, you got to have some way to still supply energy when it's dark or when there's no wind. So one of the things that engineering technology people are working on nowadays, next slide. Oh, let me just back off. So solar energy, this is just this, there's the solar panels on the house, excuse me. And on the right is a set of curves that show where the solar energy is greatest. And as you might guess, it's greatest at high noon, at noon. And also it depends on the time of the year. So in June 22nd, which is the first day of summer, that's where it's the highest. And then it drops off as the days get turns to darkness. And then in the winter, you don't have much solar energy at all, but you do still have solar energy. So it's intermittent. So just keep that in mind. We'll come back to that in a minute. Next slide. The wind, that's also intermittent. And engineering technology people work on developing windmills. That's a schematic here of a windmill, number one, which then goes, there's a generator up in that windmill that generates electricity. And then there's a transformer which converts that high voltage to, or actually increases the voltage. And then it goes to a substation, which increases the voltage because power is transmitted best at higher voltages, but then you got to eventually lower it and when it gets to the house. So this is, again, wind power, again, intermittent. It's not always windy outside. Next slide. So the big thing here is, this is really where the future is, I think, for engineers and engineering technology people, is what I call the battery boom. And what we're seeing is, if you can have batteries that can store that intermittent electric power, then you can use those batteries to take the power that was generated when the sun was highest or when the wind was blowing and store that energy and then distribute it when you need to. And you can see in this curve here, or this bar chart here, you can see how it's going up exponentially in terms of the amount of energy that can be stored, and that will continue to go up, and that will help balance out the load, or the need, not the load, but the need for energy when the sun's not up or when the wind's not blowing. So one of the things that's been developed, next slide, is this here. We've all heard of Tesla. They make electric powered cars, and Tesla said, well, you know, if we could make batteries for cars, maybe we can make something called a power wall. So what you see there on the left is a Tesla battery, and they're selling these now, that you would install in your house. And let's say you had solar power in your house, you wouldn't have a windmill in your house, but let's say you had solar panels, which you saw before. You would be using the electricity generated by them when the sun was high, but then at night you would take the energy, the excess energy that was generated by the high sun, and store it in that battery, and then that would distribute it to your house. So that would take that intermittent electricity and level it out. Next slide. So electric cars are in your future. Now, I always have a problem sometimes where I see these ads that say electric cars have no emissions. Well, the car itself doesn't have any emissions, but you had to generate the electricity somehow. Having said that, I think if our society moves both towards the small nuclear reactors and the ways to store energy from the sun and from the wind into batteries, then you really have a pretty interesting situation where electric cars are very, very energy efficient and certainly minimize any kind of pollution. So you go to the next slide. So here, what I have here is, this was calculated by the U.S. Department of Energy. We're going to compare the fuel cost for an electric car based on 12 cents per kilowatt hour. That might be a little bit more today. And gasoline, $2.67 a gallon. So for the same amount of driving, you would use, I think this is based on about 18,000 miles a year. You would use about 300 and, about $350 worth of electricity, but for gasoline, you would be up to over $750. This is just an example for one particular kind of car, but not comparing apples to oranges, comparing to the same amount of mileage for a car. Next slide. Okay, so the other thing we're interested in besides the fuel cost are what we call GHG, the greenhouse gas emissions, the pounds of CO2 that get put up into the atmosphere. So this is based on generating electricity using natural gas, and then on the right it's gasoline. So you're going to have substantially less greenhouse gas emissions with electricity than gasoline. Now, if we go to those solar power, or if we go to wind power, or if we go to the small nuclear reactors, that greenhouse gas emission will go down to essentially zero. Okay, so that's one of the reasons why electric cars are in your future. Next slide. One other thing I just want to tell you tonight, something you do when you go home, oh, you are home, I guess you're home, is the following. On the right is the typical light bulb that's been around for over 100 years now. I'm not going to say it was invented by Thomas Edison, that's another story, but Thomas Edison was really the guy that popularized the use of the incandescent light bulb. So what we're going to do is compare lighting with three different kinds of ways to make light. The incandescent light, which, if you touch a light bulb, it's hot. And so a 60-watt light bulb lasts about 1,200 hours. Well, you can get the same amount of light from what we call a CFL, a compact fluorescent lamp. You've all seen those fluorescent lamps that are in offices, those long tubes. Several years, actually about more than several years ago, about 10 years ago, they learned a way to make them so that they could be spiral like you see there. And for that, get the same amount of light, it lasts 8,000 hours, and it only uses 13 to 15 watts of electricity, which when you compare it to the 60-watt light bulb, it uses 75% less energy. But the thing you really want to use nowadays, and if you get one thing out of this talk, is to do the following. You want to take all the lights in your house that were normally either incandescent or even compact fluorescent lamps, and change them to the LED lights. The LED lights, they last 25,000 hours. And I'll tell you a little story about that in a second. There's no mercury in them. Mercury is poisonous. You got to be a little careful about that when you throw them out. There's no mercury in them. And they only use 6 to 8 watts to get the same amount of lighting that you get from that incandescent light. So it uses 84% less energy. I have an outdoor light at my house, and we leave it on all the time because it uses almost no energy, and that way we don't have to remember to turn it on or turn it off. We just leave it on all the time. And in my house, most of my lights today are LED lights. So this is all things that engineering technologists working with engineers have pioneered. So this is just a small, a really small capsule of some of the things you could be working on as a engineering technologist. And I think the real opportunity for engineering technology is the work in batteries and coupling them up with solar energy and wind energy. I think that's my last slide, Colleen. Okay.
So Dr. Reiser, if you want to take it away and talk a little bit more about the major itself.
Okay, the engineering technology, it looks a lot like engineering, except we don't insist on quite as much math. There's trigonometry or pre-calculus and one calculus class, but that's close to the end of the math you need, but you'll use it to analyze problems later in the curriculum. There's 2 physics courses, a chemistry class, a statistics class, the introduction engineering, which meets with the engineering technology engineering, 1 class for incoming first-year students. Take engineering graphics, because again, these days computer design is a big deal and you'll use the graphics more than you expect. We have 10 required courses and 8 technical electives, which gives you a lot more flexibility than you get in any of the other majors. The construction engineering technology students have the same base as the ET students, but they have 15 required courses and 3 technical electives. So they're more specified in the courses. They're pretty closely aligned with civil engineering, and most of the CET grads end up as some sort of construction project management position. So they have a much narrower path forward than engineering technology. And of course, all the options you get mean you have to make choices. It's one of those things that, yeah, we give you all this freedom. Now you got to figure out how to use it, and we'll give you as much help as we can and give you advice whenever you ask, for sure. But that many electives mean you have to give some thought to what you want to do. Now, I view my goal as being giving you enough theory so that you know why you make technical decisions, and enough hands-on work so that you know what the production staff at any place you might work will, what their concerns are. And in the old days, there used to be the design suite and the production people, and the designers would take a design and they'd essentially, we'd refer to it as throwing it over the wall to production. They almost never talk to each other, and the production people would say, what are they designing? Well, I think that engineering technologies grads are the perfect communication person to talk to both the designers and the production staff. They need to know enough about both so that they can communicate with both sides and suggest improvements, work towards making the design changes from the designers work in the production, and also take the production suggestions back to the designers to get other things to happen in a better way so that the production's smoother and fewer disruptions, things like that. So engineering technology is about both theory and practice, but we give you more practice and less theory than the engineering programs. And we hope that that makes you, again, what I say is the perfect communication person in a production environment to understand both design and implementation.
Okay, thanks, Dr. Reiser. Can you give an example of, I know our our engineering students do senior design. So do engineering technology students do something similar? Can you give us some examples of that?
Yes, we have a 1 semester capstone course. And so it's the sort of the last class, although most of my students end up taking some technical electives the same term. But the capstone class for us is a compressed senior design program. Senior design runs as either a 2 or 3 course sequence, depending on exactly how you count. We have a single semester with a team project, which means we run like crazy. It's a shorter term you don't have a lot of time, and so I try and prime the pump a little with students who I know are getting close, and work with them in the professional seminar to start planning on picking a project that they can get done in a semester. And so they have to do enough thinking about what can I do to build, what can I build in one semester with 2 or 3 teammates to demonstrate that we understand the engineering that we've learned as an undergraduate. So it's very similar to the senior design, but shorter term. So it's typically a smaller project, much more focused and not quite as complicated.
Can I add something here? Is it right, Colleen? Can I add something?
Yeah, of course.
Okay, so there's a very important thing in engineering and engineering technology education. It's called accreditation. There's an organization called the Accreditation Board for Engineering and Technology. And all of our, both our engineering technology program and our construction engineering technology program recently went through, it's every 6 years, recently went through a reaccreditation, and we came through with flying colors. That's number one. Number two, at the risk of embarrassing Professor Reiser, I will tell you this. I'm the senior associate dean, so I get to see, we survey a lot of our professors and the people who run our programs, and almost 100% Professor Reiser, who runs the engineering technology program, gets the highest evaluations among student satisfaction. He's been doing this, what, about 5 years now, Dave?
Well, I've been on main campus for 5 years, but
Yeah.
I'm teaching for 15.
Yeah, but yeah, we had something up at a community college up in Carbon County that Dave started at. We brought him down 5 years ago to really, to be honest with you, the program was kind of floundering at the time. It was almost like an orphan program, and Dave breathed life into it. And as a result of it, our students get fantastic job offers. He has a whole bunch of professors that teach in it, but he's the boss man, and I'm really proud of what he's accomplished. And if you come here and study with this, you'll have Professor Reiser, who really, I would say, Dave, you know every one of your students personally. I mean, you really
Close.
Well, I think I think it's closer than close. So you have that's going back to what Colleen had mentioned, that it's a relatively small college in a big campus. Engineering technology is a relatively small program at the engineering college. So you really get a personal connection with Professor Reiser and his staff. So I'm really proud of what he's accomplished. The Accreditation Board for Engineering and Technology was very supportive of what we've done. So we have a really good program, and as one of the senior administrators at the College of Engineering, I'm real happy about that. So I don't see your face turning too red yet, Dave, but you'll remind me of that next time we have raises, which could be 10 years from now, but things are going.
That's possible. The best news is that the program is growing, and so we aren't at all, even though we're small, we're not at all in danger of losing support of the administration. So we're in a really good place to get better, and it's looking up. I've got 2 or 3 new courses that I've launched or almost launched, and working on a hands-on component on every course I add if I can. And so it's we get more students, we get more courses that we can run as electives. So it's getting better.
Yeah, and then when Professor Reiser talks about getting better, there's a concept in engineering. It's actually in all fields, but it's really important in engineering. It's called continuous improvement, and our accreditation board requires that we show continuous improvement, and continuous improvement comes from a regular assessment of what we're doing, what the students are learning. And while we think our program's good today, it'll be better next year, and it'll be better 2 years from now. It will continue to get better. That doesn't mean it's bad, but we're always looking to improve. And that's across the whole spectrum at the College of Engineering. Continuous improvement is a real keystone tenet of what we do in the College of Engineering, both in our engineering courses, engineering majors, and our engineering technology majors. So I'm pretty pleased where we are right now, to be honest. Okay. Colleen, next slide. Okay.
Yeah,
Oh,
and that's a good way to kind of conclude things. So if you have any questions after the session tonight, you can see the contact information for all of our participants tonight. So myself, Dr. Brookstein, Dr. Reiser, as well as any general inquiries, you can email to the address you see at the top there, ugengr@temple.edu. Now, at this point, we'd like to open it up to questions from you all. If you do have questions, you can put those in the Q&A section of the Zoom. If you hover your mouse over the Zoom controls, you should see that option come up. So just click on that and type any questions that you may have into the box right there. But for now, I am going to stop the recording and we can go ahead and take your questions.